the system. In general, you want to find the optimal way to solve your problem. And so let's define what that really means now. And so we're going to start with value functions. We're basically going to say this V star, the optimal state value function, V star, is the maximum value function over all policies. Okay? So what we're saying is there's all kinds of different policies we could follow in our Markov chain, and what we care about is the best of those. We care about understanding what's the maximum possible amount of reward that you can extract from this system. There's all these different ways you can traverse this system. Each of your different policies is going to lead to a different evolution, stochastic evolution. We care about which of those is going to lead to the most reward in expectation. That's V star tells you not what the best policy was, but what's the maximum possible reward you can extract from the system. Similarly, the optimal action value function, Q star, tells you the maximum amount of reward you can extract starting in state S and taking action A. So given that you actually commit to a particular action, what's the most possible reward you can get from that point onwards? So you start in some state, you know that you're going to take left, but what's the maximal possible reward you can get after you've moved left? And what's really important about this guy here is that if you know Q star, then you're basically done. If you want to know the optimal way to behave in your MDP, what would you do? Well, if someone told you the maximum possible amount of reward you could get over all policies, given every action that you might take, so this is basically telling you, under all different ways you could behave, if you go left, you might get 70 units of reward, but under all different policies, if you go right, you can get 80 units of reward. Well, what do you do? Which way do you go? You go right. You get 80 units of reward rather than 70 units of reward. So this immediately tells you the right action to take. If you have Q star, you're done. You can kind of declare victory. You've got the quantities necessary to behave optimally within your MDP. So we could say informally that an MDP is solved when we know this optimal value function. So solving an MDP, you can think of as finding Q star. So let's just look at that. What is the optimal value function here? So again, we're going to look at the undiscounted case just to keep the numbers simple. And in this case, it should be fairly intuitive. You can kind of even work this out, just by eyeballing it. That if you're in this state here, should you go to the pub? Should you study? Well, if you study, you're going to get this plus 10 big juicy reward and go to sleep. So that turns out to be the optimal value. We'll see more formally how to derive that in a minute. If we go back up to one state here, we can either go to sleep and get a reward of 0 along the way, or we can study and end up in this nice juicy state with a value of 10 and get minus 2 along the way. So the value of being here is 8. If we back up one state again, we can see the value of being in this state is 6, because after a reward of minus 2, we'll end up in this state with 8. So that's the optimal value that you can actually get. This is V star in this MDP. It tells you how good it is to be in each of these states. And that tells you the most possible juice you can extract from this MDP. It doesn't yet tell you how to behave in it. To do that, there's two things you can do. Well, what we do is we basically define our Q stars now. In order to figure out what's the best action to take, we look at our action value function. So the action value function is now labeling these arcs with what's the value of each arc. So it's saying what's the optimal value of each arc. And so we know, for example, the optimal value of this arc here, that's 10. You're just going to take this, you're going to get your plus 10 reward, you'll be done. So that's the value of this arc here. The value of this arc here, we know that you're going to basically get minus 2 for taking that arc, and you're going to end up in a state that's going to get you 10 units of reward. So the value of this arc is 8, the value of this arc is 0. So now we can actually be able to make decisions. We can choose what's the optimal decision to take from here. Well, clearly you would pick 8 above 0, so you would choose to take this arc over here. Similarly, over here we didn't talk about the arc that goes down to the pub, and the value of this arc, and we'll see how to compute this in a minute, is actually 8.4. But once you've got this value, you can say, so this arc is basically averaging over all the things which might happen next, and looking at the value of 6, 8, and 10, and weighing them. And so now you can choose between, well, should I go into a state that gives me a reward of 10 units going onwards, or should I go to the pub, where I get this nice plus 1 reward now, and then still have a chance to get my 10? Well, you have to weigh them up, and it depends on the discount factor and all these other things. In this case, we see that this arc has a value of 10, this arc has a value of 8.4, so fortunately it turns out I'm not recommending that you all go and drink beer and you stay and listen to the course. Yeah, question?
There was a question earlier about infinite MVPs. You said it doesn't happen, but what happens then if you have a positive cycle? Say if pub was plus 100, would you keep going to the pub and studying for rest of your life? Or?
So I was talking about a Markov chain at that point. Okay, so if you've got, there are technical conditions under which reasonably defined Markov decision processes are guaranteed to terminate. So if you want to find out more about that, there's a great book by part3. He goes into all the technical conditions under which Markov decision processes are well defined. What we're going to talk about is largely the discounted case, because it's simpler. In the discounted case, you don't need to worry about any of that stuff. So if you do want to kind of remove discount factors and consider the case where you don't have discounting at all, then you need to consider what happens if you have infinite cycles and so forth. And there's two ways to deal with that. One of which is to look at all the technical conditions, make sure your MDP satisfies those technical conditions. The second case is basically to actually use the average reward version of reinforcement learning, which is in the extension to this class.
I think if you have a large enough reward on a certain edge in a positive cycle, even with a certain gamma, for example, if publish plus 1,000,
yes.
Yeah, even though you've got your gamma, you might still go around.
Yeah, I should have added. So there were some technical conditions to my answer earlier, which were, with certain probability transitions. With the transition probabilities we had before, it wasn't possible to have infinite sequences. Of course, if you have a self cycle with probability 1, that does have an infinite cycle that can be drawn from that sample. So you have to have, if you want to deal with discounts of 1, there's machinery you need. Let's not worry about that. Things are much easier when we have discounting. Okay.
What's the book name? Because it has a lot.
Yeah, sorry. So it's in all his books, but so neurodynamic programming, it's there. But he has his new edition. Probably the best place to look is volume 2 of his new edition of his dynamic programming.
Optimal control.
Yes, and I think it's volume 2 that has this in. Okay, so we've talked about optimal value function. That doesn't. So what we really care about, what's the thing we really care about? We care about the optimal policy. So the optimal policy, we need to understand what that really means. What's the best possible way to behave in an MDP? So we've talked about policies. A policy is just like a stochastic mapping, a mapping from states to actions that we take. And now we want to understand, well, what's the best one of these things? So far we've just talked about how much juice we can extract from the system, what's the maximum amount of reward we can get. We haven't yet talked about the policy itself. And so to understand what it means to be optimal, we need to define a notion of optimality. And to do that, we need to know what it means for one policy to be better than another policy. And so what we do is we actually define just a partial ordering over policies. So this partial ordering basically tells us, let's consider two policies, pi and pi prime. So these are two arbitrary policies. And we're just going to define this greater than or equal to operator. This is going to be some partial ordering over policy space. It basically tells us the intuitive thing, that one policy is better than another policy if the value function for that policy is greater than the value function for the other policy in all states. Okay? So greater than or equal to in both cases. So what this means is that it can't be worse, that it's not possible to say a policy is better than another policy if it's actually worse than that policy in one state. It has to be at least as good in all states for us to say that it's greater than or equal in the partial ordering. Okay, and then there's this very important theorem which you'll find in Patama and all the important texts on MDPs. And this basically tells us that for any MDP at all, there is an optimal policy that is better than or equal to all other policies. So you should think about that. It's like, wow, okay, this is a good thing. You don't end up with this weird situation where, sometimes you need to think about taking this policy for a little bit of the MDP and this other policy for a little bit of the MDP, and that combination might be better. There's always one unique policy. There's always at least one optimal policy pi star, not necessarily unique, that is better than or equal to all other policies. So there is always an optimal policy. This pi star tells you one way to behave in your MDP that will extract the maximal juice from that MDP. And we've already seen that that's true from the Q star. Like if you have Q star and you pick the action that chooses the arc with the biggest Q star, that gives you one such policy. Okay. But the theorem basically tells you that that's true for any MDP, that this really is the best thing that you could find at the MDP. There's not going to be some other thing that's better, there's not like some weird averaging policy that's going to do better than this. Furthermore, it is possible to have more than one optimal policy. So it's possible that, for example, the simplest case is that imagine there's one action in your MDP where there's two separate actions that take you to the same state. It doesn't really matter which one of those you take, you're going to end up in the same state. They both can be optimal. It doesn't matter which one of those you choose, you're going to get the same optimal value out of this MDP, whether you go left or go right. Okay, so there can be more than one optimal policy, but if they are optimal, then all optimal policies they extract the same amount of reward from the system. They get the same amount of juice. So the value functions for those policies are the same. And specifically, the amount of value that they get can be given by the optimal value function, by the optimal action value function here. Okay, so the value of pi star is actually exactly the optimal value function that we defined earlier. So the V star and the Q star that we defined in the previous slides are precisely the numbers that you extract if you try to evaluate the optimal policy. So if you look at how good the optimal policy is, then it is indeed the maximum amount that we thought we could get out of the system. So this is like a sanity theorem, like that all the things you would hope to be true are true, and that everything is sane, and there is this thing called an optimal policy, and it does give you the maximum amount you can get from your MDP. Okay. So how do we find this thing? Well, we've already seen this intuitively, so this is just writing it down in equations. It's just saying that all we need is you solve for Q star, and then you pick the action that gives you the most Q star. So in every state, what you do, if you're in state S, well, you just pick the action A with probability 1 that maximizes Q star, and that is the action that will give you maximum possible reward. And there is always a deterministic optimal policy. So not only is there an optimal policy, but there's a deterministic optimal policy, and this gives you one such deterministic optimal policy. Okay, and the good thing about this is, once we've got Q star, we're done. The game is solved, we're happy. So let's do this one last time back at our student MDP. So now what we're going to look at is the optimal policy. So now what we're looking at is these arcs, remember, represent the actions that we can take. Like we can study, or we can go into Facebook, we can study, or we can go to the pub. And these red arcs now are highlighting the optimal action value, the optimal policy, pi star. It's highlighted in red here. This is the undiscounted case again. So it's just this simple path all the way through our studying and studying and studying again that we'd already identified. But we can see that it must be the case again just by looking at the Q star values, which are also highlighted, and seeing that the optimal policy is always the one that picks, but whenever you've got two choices, it picks the one with the highest Q. So specifically over here, we've got the choice between Q star equals 10 for studying again, Q star equals 8.4 for going to the pub. So the optimal policy, the red arc, is the one that maximizes that and gets us the most reward going into the future. Okay, so how do we arrive at this Q star in practice? How do we actually arrive at figuring out these Q star values? These Q star values we've seen time and again, they're central. This is the central quantity we're trying to figure out so that we can just bang, pick the right action without even any look ahead or further thought. So once we have Q star, we're done. We've solved the MDP, but how do we arrive at Q star? So intuitively, what did we do? Well, we kind of worked our way backwards. We started off at this final state. We looked at the value of taking this arc, which was kind of trivially 10. You go to here, you finish, you get plus 10 along the way. And then we worked our way backwards, and we kind of did this look ahead with a one-step look ahead, where we started here and we said, okay, you start here, you look ahead one step, you end up with 10, work your way backwards. And that working backwards is precisely what we get out of a Bellman equation. So now what we're going to talk about is the Bellman optimality equation. So if you just open a textbook and hear about the Bellman equation for MDPs, they're talking about this one, not the one we looked at before. It's the Bellman optimality equation. This is the one that tells you how to really solve your MDP. The one that tells you, how do you relate the optimal value function to itself. So before we looked at the Bellman expectation equation for MDPs, which told us how V pi related to itself. So we looked at, for example, under this average behavior policy where you might go right or left with equal probability, how did the values relate to themselves. Now we're looking at really the optimal values. We're looking at the best things. We're looking at these, something like these red highlighted guys, like the values in these circles now, 6, 6, 8, 10. The maximum amount of juice you can get from your system, how does that number relate to itself? And what we can do is do like a one-step look ahead again. And so the way to understand this is, again, by this one-step look ahead, you can ask, well, what's the optimal value of being in some state? Well, you can consider each of the actions that you might take will take you to one of these chance nodes here, one of these action nodes. And we can say, when we reach that action, we can look at the action value. This is the red arc, the number on the red arc. We can say, this had a number on the red arc, which was 8, and this had a number on the red arc, which was 10, or whatever it was. And now what we do is, instead of taking the average of these guys, we take the max over these guys. So we're basically saying, look at the value of each of the actions you can take and pick the max of them. And that's going to tell you how good it is to be in this state here. It's simply the max of all the Q values. I can go left, I can go right, I look at how much reward I get in each case, and I pick the one that gives me the most. Okay? So the value function of a state is the max of the Q values of each of the actions you can take from that state. Okay? Now we're going to do the other half. So remember, we had V going to Q, now we're going to do Q going to V. So now we want to know, well, how good is one of those red arcs in that diagram? How do we know what the optimal value is for being in a particular state and taking a particular action? How do we know that the study arc has a particular optimal value to it? Well, again, we can do a one-step look ahead, but now we're looking ahead over what the dynamics might do, what the environment might do to us, where the wind might blow us. We don't control this. This is like going to the pub, and then we don't know what will happen in the pub. It's a crazy place, and we might end up in all these different situations. And each of those states that we end up in has some optimal value. And so we kind of, this is like an inductive argument. We sort of assume that we know inductively the optimal value of each of those states that we might end up in. And if we know the value of each of those states that we might end up in, we just need to average over them now. There's no max here. We don't get to pick where the wind blows us. We have to average over all the things the environment might do to us, and that tells us how good our action is. So our action is, the optimal action value is just the immediate reward plus the average over all the probability that the wind might blow us left, the probability the wind might blow us right, multiplied by the optimal value of being in that state. Okay? And again, what we can do is put those two pieces together. And when you put those two pieces together, you have a recursive relationship that relates V star to itself. So this gives us an equation that we can solve. Okay? So this is now a two-step look ahead. We're looking ahead over the actions we can take here and maximizing over those. And we're also looking ahead over the dice that the environment might roll. And we don't maximize over the dice. We don't control the dice. Instead, we average over the dice that the environment can roll. We do this two-step look ahead over our actions from this state and all the things the environment might do to us. And then we look at the optimal value of where we end up. We back these things all the way up, and that tells us how good it is to be in this state here. So that's the Bellman optimality equation of V star. Okay. So finally, just before we give one last example, we can do the same thing, flipping the diagram around and starting with the action values. And this is to arrive at a recursive relationship between the Q star values and themselves. So this isn't really saying anything different to the previous slide. It's just like a reordering of the same idea. And the reordering tells us that if we start and we want to know how good is one of these arcs, like how good is it to be in a particular state and take a particular action, now we first of all consider where the wind will blow us. We average over the dice which the environment's rolling, and wherever the dice roll, we get to make a decision. So wherever the wind blows us, we get to decide, pick one action after that, and we get to maximize over the decisions we take. So we average over the dice that we roll, and we maximize over the decisions we take, and for each of these leaves, we consider the action value, the optimal action value, like how good is it to be in this state taking this particular action, or in this state taking this action. We back that up all the way to the beginning, and that tells us the Q value of the root of this diagram. Okay, so let's make that concrete by picking one state in this diagram. probably absolutely sick to the teeth of this student MDP by now. Anyway, I promise it won't come up too much again. So here we start off in this state. We have two possible actions that we can take. So this one's rather straightforward. There's no noise that in the environment. We're not considering any dice rolls. It's just like people said before. Implicitly, there's like the environment always rolls the same way and takes us here. If we take this action, the environment always rolls the dice the same way to take us here. So we're just looking ahead one step by saying that the value of this state, 6, so this is V star of this state, 6, is equal to the max over all the things we can do here of the value function of where we end up. So we know that inductively, if we assume that these other values are correct, then we assume that this has an optimal value of 6, this has an optimal value of 8, and so if we maximize over all the things we can do, we see that oh yeah, there's a -2 along the way as well, that's why minus doesn't work. So you can either get -1 followed by ending up in a state with 6. So this has a value of 5. If we take this arc, so Q star of this arc is 5, or this way, we get -2 from our 8, and we get 6. So we choose to go this way, and our value function is 6. Okay. So how do we solve this in practice? So previously we saw that we had these Bellman equations with expectations that we could just solve by doing a matrix inversion. So that's very appealing for those of you who like MATLAB and these nice tools where you can just type in your matrix, type in your vector representing the rewards, and bam, do your matrix inversion, you're done. Unfortunately, that doesn't work for optimizing the Bellman optimality equation because we have these nonlinear equations now. We've got a max in addition to our expectation, and we want to solve for this equation that relates V star to itself or Q star to itself with a max over these expectations. So in general, there's no closed form to this thing, and we have to be smarter. And how do we be smarter? Well, using iterative solution methods, of which the best known examples are value iteration, policy iteration, which we'll talk about in the next class. These are dynamic programming methods for iteratively solving these recursive equations. And Q-learning, which we'll talk about in a subsequent lecture.
The matrix solution itself is implicitly iterative underneath. You don't get away from doing any sort of iterative calculations. I mean, to solve that matrix equation, it's still an order n cubed problem where you have to iterate in some sense to get the solution.
Well, I mean, there's computation required to solve the matrix, and there's steps to that computation. Right. But it's not. So by an iterative solution method, we mean something more like where you have an equation which you iteratively apply. At each step, you apply the next step of that update. So you start with some estimate, you update your estimate towards a new estimate, and so forth. Now, of course, there are iterative approaches to matrix inversion, like the Sherman-Morrison trick, which can be applied to reinforcement learning as well. And so there are cases where the matrix inversion can be reduced in complexity from n cubed to n squared. Those are special cases, and so I'm talking about the general approach here. So yes and no. Okay, so we're just about out of time. I think I want to really just take questions and make sure people are following rather than going into the extensions in any great detail. So this is a great time if you feel that something was unclear, and now's your chance to ask. Otherwise, I'm just going to assume that that's all the notes were incredibly perfectly clear and everyone understood everything, which I'm very confident is not true. Yes, please.
So if you have an imperfect model or have missing information, how would that translate to your diagram of the MDP? Would you have missing nodes, or would you have a uniform distribution where you should have a different one, or the environment dice roll?
Okay, so it's a great question. So the question is, in reality, the MDP is just a model. We're trying to model some real phenomenon out in the world, some real environment. How do we represent the fact that our model is imperfect? We're actually going to have a class on where we'll talk about model-based reinforcement learning. If there's time, I'll talk about some of the approaches to uncertainty. So some of the classical approaches to uncertainty include explicitly representing the uncertainty in the MDP. So you could be Bayesian, for example, have some posterior estimate of what the MDP dynamics are, and then solve not just for one single MDP, but for a whole distribution over MDPs, and find the policy that's optimal with respect to all of them. That's computationally very difficult. Another approach is to actually factor in the uncertainty in your representation of what's going on in the world into your MDP itself. So you'll say you're in a state where not only am I in a state where my robot's here, but I'm in a state where my robot's here and I think that the world has these dynamics, or I'm in a state where the robot's here and I've seen these observations so far which implicitly tell me something about the uncertainty of what's going on in the MDP. So that can be much more tractable. You don't necessarily need to explicitly reason about all the uncertainty in the environment, but it's maybe a little less intuitive to understand the form of the uncertainty. The uncertainty isn't made explicit. And then maybe the only other thing to say, which we already touched on, is that sometimes it's sufficient to just say, well, accept that that our model is imperfect, and use a discount factor to capture the fact that we've got some uncertainty. You can also make the discount factor variable to represent the fact that you're more uncertain in some states than others. So you don't have to have 0.9 everywhere. You could have 0.9 in one state, 0.99 in another state, representing how bad your model is in that situation. So it's a very active research area. I think it's a great question. Yeah.
So everything we've shown us today seems to sort of geared towards like maximizing reward.
Mm-hmm.
But is there anything implicit in there that would also like have a consideration of risk? So like if you might be interested in maximizing your reward at a future time and choosing that policy, but there might be some chance that choosing that policy, that there's also an increased risk.
Okay, so the question is, everything's just talking about maximizing reward and expectations of those reward without explicitly considering risk or variance of those returns. So I think the correct answer to that is to say that you can always transform any MDP with no risk into, so if there's some amount that you care about your risk, like let's say that there's a cost that depends on the variance of your returns, there is another MDP which has a different reward function that already factors in the variance of those rewards into the actual reward that you see at the end of your trajectory.
So that can be implicit in this model you've shown us today, basically.
So there is a transformation of any risk-sensitive MDP into another MDP. However, that transformation can be quite complex. So you might need to remember all the things that you've seen so far, and it can be a more complicated MDP that you end up having to solve. So that's the first answer. The second answer is to say that a bunch of people do specifically consider risk-sensitive MDPs, where you don't just consider expectations, but you consider what's the variance of those rewards at the end of the day. So there's a bunch of work out there, and I'm happy to give you pointers to that if you're interested. Any other questions? Okay, one more, and then I just want to say a couple of words before everyone piles up. Oh yeah, sorry, this guy was actually waiting for longer. So.
Some example for intuition for the Bellman equation, for instance. Obviously you have two parts which balance, and I think it's just pure mass. There are situations, for instance, in finance where somebody will actually balance it, in terms of arbitrage. But in terms of like real equation, real situations like a robot or like a tie game, what does it make it sort of to actually hold true?
Okay, so the question is, what's the intuition behind the Bellman equation in some real example? So if we take the Atari game as an example, so the Bellman optimality equation, let's focus on that one. That's the crux of where we got to. The Q star or V star is telling you, what's the maximum amount of score you can get. You're in this screen here. What's the maximum score you can get from this screen here? And the intuition is that all you need to do to get that maximum score, this is called the principle of optimality. So the principle of optimality tells you that the way to get the maximum score is to behave optimally for one step, and then to behave optimally for the remainder of your trajectory. Okay? If you behave optimally for the remainder of your trajectory, that's the value function from the state that you end up in. And so now all you need to do is to figure out, well, how do I behave optimally for one step? And the way that you behave optimally for one step is to maximize over those optimal value functions in the places you might end up in. So it's like you might move Pac-Man to the left, and you might move Pac-Man to the right. If you move Pac-Man to the right, and you can get 100 points of optimal value from that point onwards. Or so moving to the right, you might get plus 10, and then 100 points of optimal value afterwards. Moving to the left, you might get plus 20, but then only 50 points of optimal value afterwards. And so the intuition is that just by breaking down your trajectory into these two parts, into the optimal decision at one step and the optimal decision from there onwards, you can describe what it means to have optimal dynamics for the whole problem. Okay. One more question, then I just want to say a couple of words about the extensions, but without any details at all, so don't get scared. Yes?
In terms of practical applications, say you have a million states and a million actions per state, how do you arrive at the rewards?
So if you have a million states and a million actions per state, you have a large MDP, and so now you're asking how do you actually solve the MDP to find the optimal value function? Is that the question? Was the question how do you solve it, or how do you decide on the immediate rewards?
How do you model the rewards? Probably not manually typing everything.
I see. So the question isn't how do you solve the MDP, it's how do you model the MDP? How do you represent a large MDP? So typically the reward function is given by the environment dynamics. So it's given by so for example it might be, imagine you're playing Atari. The score that you get, there are many more than a million states in Atari, and yet the score is just a function of that state that you're in. So it's something which, you're in this state, you query the emulator, you say what's the score, or you extract the score from the screen, and it's just a function that depends on your state. So typically there's some function mapping state to reward, and that function characterizes imagine you're a programmer and you're trying to tell your program what the problem is you're trying to solve. The reward function is kind of like the definition of the program. You're asking the program to solve this particular problem. It's part of the problem definition. So the reward is just a function it's part of the environment. It's part of the thing describing how the environment state gets mapped into reward. So in any reasonable problem, you'll see that there's a way to transform this and describe the reward, normally quite conveniently. There's a big open question, which is how do you best model the reward in the way that actually leads to intuitively what we as humans think of as the best solution. Okay, very briefly, I just wanted to put up this slide just to highlight that there are some additional slides, extensions to MDPs. This is not examinable material. I do not expect you guys to go off and revise stuff which I haven't told you about. And in general for these classes, I'll try to make it very clear what's non-examinable material. And if we run out of time at any point, don't panic. You won't suddenly find a question that crop up in the exam which we didn't cover. But the extensions are on the slides just there as additional material, in particular telling you how to deal with infinite MDPs, continuous MDPs, partially observable MDPs, undiscounted average reward MDPs. These are the major extensions to the MDP framework. Just to give you some sense, I think just out of interest you can get some sense. It's not details, it's just a brief outline showing you how you can move beyond this to the case where you're trying to control some real aeroplane or helicopter with continuous actions and perhaps even continuous time steps, or where the state that you see doesn't tell you everything about the environment, but you just get to see the robot's camera at every given time step, and you don't get exposed to the Markov state that's actually inside the environment. You just get to see what your agent sees at that moment. And finally, the case where we can deal with undiscounted case by basically looking at a limiting case where we average over, where we look at the average reward going into the future, the average reward per time step, instead of the discounted sum of rewards. It's a different definition of return that actually works out very neatly. So just if you're feeling enthusiastic, go and have a look. There's pointers to elsewhere. And otherwise, the remainder is next week we'll start to talk about how to solve these things. So this is just defining the problem.